Bom dia, good morning. So let's continue with now some numerics, right, for waves in sort of disordered medium. So today I'm going to talk about this other article, which is also with Juan Carlos, my first student. And the title is SIAM journal called, doesn't have SIAM in the name, it's called Multiscale Modeling and Simulation. And it was 2005. So you can see the title. Now we were then looking at numerical aspects from that other paper that I showed last class. Okay, out of Juan Carlos' thesis. So it's the same equation, okay, the same equation. And today I'm going to start talking about the conformal mapping. I'm going to show you some of the things conformal mapping. And in this paper, we were interested in two things. First, showing that actually conformal mapping helped us also in the numerics, which is quite surprising. We weren't even thinking about it. And then suddenly we see that, whoa, it looks like conformal mapping is helping us. I'll show you how. And also, the second part is a part that I mentioned. I think I didn't mention this course. I sometimes mention in other courses, which is another very fascinating phenomena of waves in disordered medium. And I'll mention just a little bit, which is this solitary wave refocusing. That I'll mention very, very quickly. It's really, when I saw this for the first time, it looked like a little bit like science fiction. You know, you don't have a physical intuition, you don't have a mathematical intuition, and you say, how in hell is this happening? And it's beautiful. So I'll tell you just a little bit about that. Okay? So, what I want to say, let me get the pointer, I forgot, is this. We started with this equation here, okay, because we wanted to solve a problem where we had a topography like this. Because, why? Because we wanted to use the technology, mathematical technology from acoustic waves, right? And I'm not going to draw acoustic waves anymore because, you know, it's a stratified medium. But as mathematicians, right, we say, hey, the acoustic waves look like the shallow water equations for this bottom hyperbolic system, piecewise constant coefficients, blah, blah, blah. So that's how the mathematicians work, right? And that's the nice thing about applied math and modeling, because sometimes you say, this model here looks very much like that model over there with nothing having to do, right? So, okay. So, and then here we can have see, here we can have a dispersive perturbation, which I did last time, and also a nonlinear perturbation to what the acoustic people did. The first one we did was the dispersive perturbation. But you know, there already existed, you see, there already existed a Boussinesq model along the lines of this one by a very well-known, famous researcher, and unfortunately passed away. He actually visited IMPA at one point, Howell Peregrine, who was from the University of Bristol and actually an editor of the Journal of Fluid Mechanics, super important guy in fluid mechanics. And he had a model, Boussinesq model, but for a Boussinesq equation, I'm going to show you his model in just a second, but for smooth, mild slope topographies. So the model is like this, mild slope bottoms, okay? So this is my bottom, the bottom of our model. This is Peregrine's. And what does it mean, mild slope? I think the name speaks for itself, right? Does it make sense for you, just checking? Mild slope, right? So mild means slowly varying, means, easy going, right? In a colloquial, informal way, easy going. Slope, so the slope is not too large. It's mild. It sort of varies in a smooth and slow kind of way, okay? So this means these slopes here are small. The derivative is small. And therefore, then Peregrine in 1967, I think it is, I'm seeing the reference, so some time ago, Peregrine, 1967, yes. He deduced this model, well-known model, very nice with variable bottom and so on. And I'm going to show you his equations, okay? And it uses similar technology, but they I think, expand about the bottom because this is slow and small derivatives. And here, as I mentioned, even if it was smooth but rapidly varying, okay, and this is something we see, as I mentioned, in PDE's course, you can't do the expansion because the bottom here that I'm interested, sometimes it's like this. Even if it's smooth, here it's even worse because it has corners. But if it's smooth, if I take derivatives of this guy, I get terms 1 over epsilon in front. And that messes up my Taylor series expansion. Where here, you have something more like this. The derivative is small. It pops an epsilon in front. Okay? So, but then I thought with one concept, let's check something. Let's compare our equations with the equations for Peregrine, and let's put a smooth topography in our case to see just the effect of the change of variables, that is, of the conformal mapping. Okay? So I have the equations there. I think I should copy it here. I don't know, even though I work with these equations, let me write it over here. No, it's eta c, because I'm going to soon have the Peregrine's equation. So that we can compare okay, so this is our equation. And now let me put here the Peregrine's equation. Let me see here. Como é que eu pagino aqui? Ah, mas aí diminuiu. Obrigado. Ok, obrigado. Well, this is our equation. This is the conformal mapping. So you see the conformal mapping, we can even do for a bottom that's not single valued, right? Like we say in Portuguese, a marquise with a roof and everything. Even though this is just to show for fun, we didn't use a bottom like this. And let's see now Peregrine's. And here's Peregrine's equation, mild slope equation. Okay, so let me write it here for comparison. No, maybe not. Let me save us time. I don't think I have to write it. So compare this. So this is mathematically, okay? So basically what I'm saying is this. We're going to do a test what I'm going to show you in just a second is now a test like this. Suppose we have a periodic bottom, okay? I'm exaggerating here just for the drawing. It's mild slope, okay? And I'm going to compare Peregrine's equation, which is in x, y, with our equation, which was deduced in xi zeta, 8 zeta, okay, which is this. The terrain following coordinate system. Okay, so this is the xi zeta, okay, and this is, let me put it like this, x, y. So you can write the equations in both coordinate systems, right? Either one or the other one, which means one is in the Cartesian coordinate system, the other one is in curvilinear orthogonal coordinate system, where, because I mentioned to you that the Laplace's equation is invariant, right? So if you write the equations in this coordinate system, right? In this coordinate system, you get this equation. Okay? Now, if you do in Peregrine's coordinate system, you get that equation up there. Okay? Now, check the difference. So maybe because of the video, let me write the equation here. Maybe it's a good idea. Let me write the equation here. Eta t plus h plus alpha equals 0. Ut plus eta x plus alpha ux plus beta. I wrote too big. Well, let's see. H squared over 6 uxxt plus, no, minus h over 2 HUT. Okay? So we can then compare here. Look at the difference. So these are mathematically, they're two equivalent equations. Okay? To be fair with this set of equations, which is Peregrine's equation, I will show you a numerical simulation with a smooth, mild slope topography. Okay? The condition over there is that you see, so the condition here is that h prime over kh is small. Okay? So this is the slope of the topography, and this is somehow the slope of the wave. Right? Right? Because k is 2 pi over lambda. So this is like h over lambda, okay? Now, okay, so what do you see now, since you are, right, learning PDEs, learning PDEs and applications, learning numerics. Here there's no numerics yet, but what do you see, what calls your attention between the difference of these two equations here? So let me highlight things. Here is my nonlinear term. Okay, here's my nonlinear term. Where, what is this? This is total depth, which is h plus the wave elevation, alpha eta. Here is another nonlinear term. Okay, kind of equivalent to this one, because if you differentiate this, right, I could actually write this as, this is the same as u2 over 2x, right? So it's similar to this to some extent. So what do you see? What did the conformal mapping, or in other words, the curvilinear coordinate system do to the equation? Mathematically, they should be equivalent. They're the same regime. Weakly nonlinear, weakly dispersive, weakly nonlinear, weakly dispersive systems. Okay, and starting from the same equation. It's just that one is using a coordinate system different from the other, right? And what I'm going to show to you now is the effect of the fact that I use a different coordinate system. And what I'll show you to you, which is at first we're not even thinking of that, me and Juan Carlos, is that the conformal mapping will help us. How? Not very clear, but there's a little bit of a hint here. There's a little bit of a hint. Why is the equation, so here's the question for you, just for you to sort of start getting, the sort of feeling for where, it's not a conclusive, but where there could be some danger, okay? So where is a term that maybe, I have to pay attention. What is the difference between, in terms of mathematically, in numerics, there's a danger of one equation with the other. I can say it in two ways, of course, now that I've studied this and I learned about it, right? But first, there was one thing that already when I saw this, when Carlos said, let's find a way to explain this. And I don't even remember. I think maybe we even did the numerics before, and then said, no, look, yes, we are right. There is a problem. Let's try to explain this. I think we did the numerics first, right? In the paper, we don't put it that way, but we did, I think, the numerics first. Yeah. So let me help you, okay? Look at this. This is where my intuition, without me being able to really be precise in the beginning, my intuition started saying, there's something here. Look. First thing, remember that if I have a topography that's rapidly varying, this model was not designed for that. Okay, so that's not fair. Okay. But in any case, look, if I start pushing, and that's what we're going to do numerically, if I start pushing the topography to the limit where this is true, making the topography a little more rapidly varying, not so much mild slope, but started pushing it against its hypothesis, right? Still within the regime, but making it more and more dramatic. Well, this h is going to be starting to vary a little faster, not fast, but less slower. And therefore, derivatives of this guy are going to play a role. Where do I have derivatives of this guy? Well, here I have derivatives of the topography hidden in my Jacobian. And we saw that the Jacobian last time, as things becomes faster, it sort of averages things out. Do you remember what I'm talking about? I'll show you more pictures in a second. But if the topography is like this, very rapidly varying, the Jacobian is something like this. So that I knew. I say, hey, the Jacobian helps me in this coefficient. If something is rapidly varying, the Jacobian kind of uses glasses and cannot see things very well. So he sees things a little blurred, which is good, smoothed out. Okay? So here we see that there's derivatives, second derivatives of h appearing, which here I don't have, plus derivatives of h, and h are multiplying high derivatives of the solution. Okay? So what I'm going to do now is not 100% correct, because it's like a informal, messy, not very formal Fourier analysis, but just so you see my intuition, is that think that h is e to the I k1x, right? So something periodic. And here I have a Fourier mode for the velocity u, which is e to the I k2x. Okay? And it's rapidly varying. So basically, here I'm going to have like k1 times k2. What I'm doing is not really correct. It's just so intuition. So it's like frequencies become even faster because I'm multiplying terms. That is not correct what I'm doing. It's just to get into. So I said, how can I figure out this? So okay. So first thing so these terms here look like they're going to give me trouble, numerically speaking, and that's where we see this. Why we put this title: stiff microscale forcing, which means if the topography starts becoming faster, this system is going to show us some stiffness in some sense. Okay? So this explanation of Fourier that I did here is not good. I mean, not good in the sense that it's not the way we're going to work things out, but just to show that high frequencies here are going to sort of amplify each other because they multiply each other. That's all. Okay? So but that's not the way we're going to do it because it's very massive. We can do it. So let's first see, I think, numerically the effect of this. So numerically, I think it's the first thing I'm going to show. So here's the coefficient. Yeah, here it is. So the first thing we show, which is fun doing with the conformal mapping, which we're going to start seeing today, is that if I have a periodic topography, which is slowly varying, it originally has corners. Because it's like triangular mountains, as a simplification. But when I do the conformal mapping, and we understand this with doing some theory with it, I mean, but this is not a theory course, right? Basically using Green's function, blah, blah, blah. We can show that actually it smooths out the topography. And here is a verification of that. Look at that. Look that over the crest of the mountains, you see it's smooth. There's a little mild shaving of the corner. And over the valleys, in the valleys of the topography, it does the same thing. But overall, the mountains are the same, right? The waves don't feel that little minor change in the topography, minor regularization of the topography, right? Almost like also we used in PDE's language when you have a singularity, a mild mollification, right? When something becomes C infinity. This topography, the smooth one is actually C infinity because the Jacobian is C infinity, but it looks very much like the original one that's continuous by parts. Okay, fine. Okay, so that's good. So now we're going to do a test with this topography with both models. Here it is. So here it is with both models. But you see, because the coordinate system is not the same, here the solution looks a little bit, there's a difference of position. So we put them in the same coordinate system, right? Because one is in Xi, the other one is in X, right? So note here, one is in Xi, the other one is in X. And when we do the conformal mapping, this domain here gets stretched into a flat strip, so there's a rescaling of positions, okay? So then if you come back and then put both of them in the same scale, you can do that with the conformal mapping. Here it is. It looks like good news. One solution is right on top of the other. So one solution here, I forget who's who, you're going to see in just a second. Solid line or dots, I don't know which one is which one. I can check in just a second because the legend is below. One is for Peregrine's equation, and the other one is for our equation. So they're doing the same thing. And you see the Airy function, you see the dispersive tail, it's very dispersive, and you see a little bit of oscillations below. But now let's do a zoom into the solution. You see what I mean in just a second. Let's zoom in. And here's what see. So look, the model, the dashed line is our model, and the solid line is Peregrine's model, 3.1. And look what's happening. You see a little bit of noise, right? Like round of error starting to contaminate the solution. You see, it's noisy. Do you agree? See where it's noisy? And that is to us an indication exactly of that the fact that we are pushing these terms here to the limit because we're getting very close to the bound where this guy here is not so small. So we're getting to the limit where the hypothesis of mild slope is starting to be violated. Okay, so we did this on purpose. So we chose this triangular mountains very close to the boundary of where it's not a mild slope anymore. Okay, so both methods are kind of good, but you see that this formulation is starting to suffer, right? In the sense that if you look here, you say, look, Andrea, it looks pretty good. But if you zoom in, you see that noise is starting to contaminate the solution. Okay? Agree with the story? So that shows, so then we said, hey, yes, I think we did this before. Now, some years ago, I don't quite remember the order of things, but actually, I'm almost sure it was in the good spirit of scientific computing. You see in the computer and say, okay, now let me try to explain this a little bit more mathematically. So that confirmed the intuition that those terms, the dispersive term having a variable coefficient that is differentiated would eventually give a headache, right? Okay, so let me show you how we then sort of rationalize this, because this is intuitive, numerical evidence. How did we rationalize it mathematically, okay? And it's not Fourier stuff because it will be very messy. So that's what I'm going to show you. So, okay, so the way we're going to do this is let's look at Peregrine's model first. And actually, we cannot do Fourier in space, right? What I was telling you here was Fourier in space, right? This is e to the I k1x, whatever. And it's going to be a mess because this is variable coefficient. We can't do Fourier in space. So we're going to do Fourier in time, okay? So look at the analysis of how we do. So we take, and we're going to do, because we're going to do Fourier, we're going to do the linear system, right? Because we want to see the effect of the dispersive term. So nonlinearity is not at first a bad guy. So okay, so take Peregrine's model, linear version, and it looks like this. Okay? And this is the when the system is valid. So we're scaling, instead of epsilon, I'm using gamma. Doesn't matter. Gamma is a small parameter. We take a Fourier in time. So eta hat, u hat are Fourier in time. This is the system. And I want to write this a little bit, rewrite this so it looks like a ODE system in X, and so that we can see the eigenvalues associated to the matrix. Okay? So let's see how this goes. Okay, so we rewrite the system like this. Okay, it looks like something like, manipulating the system, we can write something that looks like an ODE. And we look at the characteristic polynomial of this matrix where the eigenvalues, it's like a little bit like sometimes called also frozen coefficient. You look at things locally, how the eigenvalue depends with X. Okay, and this is how the eigenvalues depend on X. Right, and depends on variations of the topography. Okay? Now, and it's this messy expression. So one thing we notice here is that, well, if H is constant equal to 1, we recover the original dispersion relation, okay, because eigenvalues we know has a connection with frequencies and so on. So if H is equal to constant to 1, all these derivatives disappear. And we see a little bit the problem here is as gamma goes to 0, that means that the topography becomes smaller and smaller. So this is the, excuse me, this is the original dispersion relation. Okay, just changing the role between K and W. Okay, dispersion relation usually is omega as a function of K. Here we just exchange the role, no big deal. Okay. But now, look at this. This is where we see the problem. The eigenvalues, if we simplify that complicated formula and write it in terms of how does it depend on our gamma, which is our parameter of the topography, okay, the eigenvalue asymptotically goes like this. Okay? So this is the real part, this is the imaginary part, and you see gamma is the parameter of how fast the topography is, and as gamma decreases, the spectrum, you're so focused, the spectrum becomes wider and wider. So we have higher and higher frequencies, which is something a bit of a headache. So we have a spectrum of eigenvalues which are on a very wide scale. Okay, and we know this sometimes is a problem for stiffness, right? So now let's do a similar analysis with the other model, right? The one that conformal map is. So here we see, look, that the real part will grow as gamma goes to 0, and the imaginary part will grow as gamma goes to 0. Okay? And here actually we got to be careful because there's a square root and so on, but this just shows, like here we have it too, shows that we have a headache. Now for this system here, right, if we do the same, okay, now instead of x we have it in c, so if we do FFT in time, we have this system, which we can write it like this. Okay, then we can get a matrix here because, right, in terms of C and of eta and U, here is the characteristic polynomial for the variable coefficient matrix, and it depends on M now instead of the topography. I mean the topography directly, depends on the Jacobian. So we get this messy expression. Here's one way of writing the Jacobian, analytically speaking. Right? So use H is 1 plus n. So n is like the fluctuation of the topography. So as n becomes more rapidly varying, you see you have this integral. That's how it does the sort of regularization. Here you have to believe this because, of course, I'm not giving you enough information. And if we, this is just some details, and if we actually look at the eigenvalues written for this guy, then it depends in this way on the square root of beta and on m. But m, as I told you from this picture here, and I'm going to show you more pictures, m actually becomes something smooth. So the eigenvalues don't grow when we do it in this curvilinear coordinate system instead of the Cartesian coordinate system. And somehow that acts, and that's what we mentioned in the paper, to our surprise, without us designing it this way, the conformal mapping acts almost like a preconditioner. It's sort of a precondition is that preconditions the system, right? And conditioning comes from linear algebra. I think some of you or most of you have heard of this, right? Condition number of a system and so on. So if a matrix, if you look at sometimes the spectral radius of a matrix, which is associated with a 2 norm and so on, if you have a very wide spectral radius, it means a very disparate range of eigenvalues, you have a large condition number, right? And to our surprise, complex variables without us thinking about it. So this came later on. We realized, wow, not only complex variables helped us. That was the first thing we tried. We used complex variables because complex variables eliminated these corners and mapped this domain to a flat strip. And then I said, oh, now I know how to do the expansions, blah, 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 all that. But I did not expect at all that it would help me also numerically, right, in terms of preconditioning. And in this paper, we realized that it was quite a surprise. Okay, again, don't feel bad if you're not following all the details, also people who are seeing on the video, because I'm going fast and superficially, but just try to understand the story, right? Because if you sit down and study, you can understand this. It's not that difficult. It's just like what was difficult for us is how do we piece together the information, what we're seeing from the computer and so on, and this is the way we did it. And so don't feel bad if you're not following all the details. You basically follow the story. That's the important thing. Okay, so that's why we called it stiff microscale forcing. Is it clear to the title? Because if we did it in Cartesian coordinates using Peregrine's model, we get this stiffness, which means we start seeing numerical instabilities and so on. And using conformal mapping, we were somehow preconditioning, removing this stiffness. Okay, that's the main idea. Let me see if I have any interesting figures to show to you, and then I'm going to move to another paper and start talking of the conformal mapping, as I promised before. Okay. So here's the numerical method we discussed last time, but I think there might be some interesting pictures. Let me see. I don't remember now of our numerics. Yeah, so here I'm just showing again what I showed to you last time, that the wave that goes through a disordered random topography, the diffusion, the post-shaping is deterministic. And here we see it. We did several different realizations, which means samplings. And you see the wavefront is exactly the same for all cases, but the coda, which means the oscillatory tail, that depends on the realization, the sampling of the bottom. So you see it's random. So very nice to see that the numerical method captures that very well. And let me see if there's something about time reversal refocusing here. This is for the solitary wave. Yeah, time reversal and refocusing. Okay, let me show you a little bit this phenomenon. This phenomenon is very much fun. In some other courses I think I mentioned, I think I never mentioned here in this course what time reversed refocusing is. Is that correct? Do you have an idea what I'm talking about? I hope not, because then it's new, right? No? Okay, you saw a video on YouTube, but not that I mentioned to you, right?
There is your collection.
Yeah, my collect. I mean, some of those quick talks to introduce. Okay, but not in the course. So this is a very fun thing, which also came from a physicist to the Papanicolaou group, and people started, Papanicolaou and collaborators, which was not me at first, doing mathematical research on this, and then with another part of the group which is with Jean-Pierre Fouque, and then his former student Jocelyn Garnier. We started working on this, and it was extremely fun. And actually, we started working on this, starting based on the work of Juan Carlos' thesis, because then I understood how things were working. And time reversal is a spectacular phenomenon. It goes like this. Take a wave, our famous Gaussian pulse, okay? And now think that from 0 to 50, you have a random topography. That is a disordered topography that was generated by a random number generator. Okay? So let me do a picture again here so I can explain what's going to happen. So we have now a medium. This is actually was studied in a laboratory. So time reversal, let me put it here, time reversal and wave refocusing started with famous French physicist Matthias Fink. Let me put it like this, physics from France, who did experiments. And he was very good friends, he is, I think, very good friends with Jean-Pierre Fouque and Jocelyn Garnier, that I worked with. And we tried to do this for water waves. So he was doing this for acoustics. So again, us getting mathematical technology imported from acoustics and doing research for water waves. Not only I like water waves, maybe because I live in Rio, beautiful beaches and waves, but mathematically they're very good because they come in with nonlinearity and dispersion. They come in with new PDE ingredients. So mathematically they're very interesting, okay? So now what were we doing? So here we put the random topography. Okay, let me finish it. Like piecewise constant, like this. Okay? And this goes to infinity, which means in theory, okay? So it's half space random. This means and you send a wave. Okay? So what happens? What happens, maybe I can go to the picture, is that as this wave travels here, it's like this. This guy is going this way, but here you have signals going both ways. Okay, that you already have the intuition, right? You agree? Right? Because bouncing back and forth. Look what happens. This is amazing. So this first picture here is my Gaussian waiting for us to start the simulation. Over here, from 0 to 50 is my disordered topography. 50 is long enough, 50 units. The Gaussian is about 1 unit long, wide, sorry. 50 units about okay for us to see the simulation, for see the phenomenon. We send the wave, and here is the multiple scattering, which means that part is going back and forth. Here is the transmitted wave surviving under apparent diffusion, as you already saw. So the diffusion is the filter that's taking energy from the front to the back. And this part here is the reflected signal. Why? Because it's over here. Look. Because it's over here. So over here, it's flat. So this wave is only moving to the left. Excuse me. I thought I was going to sneeze. Excuse me. Okay? So now, here's the time reversal. So now you stop your simulation. This is amazing. You stop your simulation. It's here. And now you do the same, you solve the same PDE, everything. But now this is your initial data. It's not the Gaussian. So you get this guy here, said, okay, it was going that way, but now it's going to go this way. That's why it's called time reversal. Like you putting a film backwards, okay? So this wave that came back, the reflected wave, now is your initial data, instead of this guy, for the same problem. And it's spectacular. The random medium, that is the disordered medium, interacting with the disordered signal that it generated, recompresses things, reorganizes things, that is the refocusing, and you see a small copy of the Gaussian. Why a small copy? Because I'm only using part of the information. Okay, with another student, Daniel Alfaro, we then did something very long, and actually we were able to recover everything. But I'm not going to show this here, I think. So, okay, so look at this now. We send this back, and look what comes out. A copy of the initial data. A copy. This is a small Gaussian, smaller than this one, But mathematically, they can prove, actually Jean-Pierre Fouque and Joseph Lagarnier proved that as epsilon goes to 0, blah, 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 if the medium is infinite, blah, 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 you get everything back with the same form of your initial data. And here's the numerics is showing that. It's amazing. Is it intuitive? To me, it was not, right? You get something that was generated by a random coefficient. That is a sampling, a realization. The realization means you sampled a random series, right? You send in the wave, which is a Gaussian deterministic, will interact with this guy and will generate a random reflected wave. This random reflected wave, if you send it back to the same topography that generated it, it will recompress, reorganize into this. So amazing. Okay, so I think I have half an hour. Let me soon start with the conformal mapping because I promised it's about time. Okay, here it's just showing theory, I think, and computation. No, 2 levels of dispersion. The other cases with dispersion, I think this is enough for here. Yeah, and here's the refocusing of a solitary wave. This is the first experiment. Let me see if I have the other one. Yeah, here's, I think, the... Yeah, this is for solitary. Yeah, let me go now to the conformal mapping. Cadê a pasta aqui? Estou me enrolando. Oi? Área de trabalho? Você que eu estou meio seguido aqui. Tá, então abre. Tá, obrigado. Opa, não enrolado, cadê a área de trabalho aqui? Meu Deus. Eu com Windows me enrolo, cadê a área de trabalho aqui?
Fecha aí, fecha. Aqui, ó. Fica até atrás disso aí.
Ah, tá aí atrás. Obrigado, quero o outro. Deixa eu ver se eu achei isso aí. Tá bom, é isso aqui.
Organizar. Módulo aqui. Aí aqui no Ctrl mais. Mais.
Então, tudo bem, deixa eu ir lá para baixo, tudo bem. Obrigado. Okay. Sorry. Good. So let me show you now some of the conformal mapping, okay, how we do this. So this is exactly the same case we had in that paper, right? So we had this triangular topography and the mapped one. Now let's see how can we construct this. Okay, so this is a talk. This is something I gave, a talk I gave in the short course some time ago. Let me actually write here on the board the references, and I'll send to you by email. Okay, whoever wants, I can send this to. So I'm going to use 2 references. This talk is something I got out of this, and I wrote a chapter in the book related to a short course, to a summer course, which is conformal mapping. and Complex Topographies. This was written by myself. This is chapter 10 in this book, which is based on the summer school lectures on the theory of water waves. Edited by Bridges, Groves, and Nichols. This is Cambridge University Press. (2016). And also, you should know the book by Driscoll and Trefethen, which is Schwartz. Christoffel Mapping by Driscoll and Trefethen. Also, Cambridge University Press, which is Coop. Cambridge University Press, 2002. These are two of the references that are useful. I'll mention more if needed. So this presentation was at the Newton Institute in Cambridge. It was a summer school. I gave like three lectures, I think, on this. And there was I wrote the chapter for the book. And let me go here for the part which is related to the numerics, and not the theory, but the numerics. Oops. Okay. So I want to do, remember that I mentioned that it's a trick, sometimes a good trick, to reflect the physical domain. So in this case here, I have a topography which has just a rectangular obstacle on the bottom. Okay, we reflect it about the free surface, which is where you have these red dots. Okay, this is a theoretical expression to extract the Jacobian. Here the Jacobian, the m, is 1, which would be the identity if nothing happened, plus this little m, which I'm calling the metric coefficient. I can theoretically write this m like this, for those who did the PDEs and applications course with me using Green's function and so on, right? But let's not worry about this. This formula is very good theoretically, but it's very hard to extract a number from it. So the conformal mapping has to be done another way, as the way done in numerics in the book. Okay, so let me show you now how it is done. The other equivalent formula. So here's the book, the first important book, which I put here on the blackboard, which is Schwartz-Christoffel Mapping. You can't quite read over there, it's not very good, by Driscoll and Trefethen, Toby Driscoll and Trefethen. And this is how it works. Now, this is a formula which is good to extract numbers, but it's bad for the intuition. You see, the other one I wrote before is good for the intuition to show, for example, that things get smoothed out, that there's this sort of averaging, blah, blah. It's good for that, but it's very difficult. I would say maybe even impossible. I don't know. It's not impossible. It's very difficult to extract numbers. This one is not intuitive, at least for me, but it is the one to extract numbers, and that's how it's used in the book. So look what this says. Let's see if this is complex variables, okay? Not numerics, and I'm not yet. So I have a mapping from a flat domain, which is this, think of this as a flat strip, okay? Where on the top of the strip, there's a line here, I'm in the W plane. So the W plane is Xi plus I zeta, okay? Because maybe the transparency is not so clear, let me put it also on the board for people to see. So I have here, for example, my plane, right? So this is Xi zeta. W is equal to Xi plus I zeta. Here is x, y, and z equals to e plus x, y. And the mapping is usually in this direction. Okay, it doesn't matter, right? The mapping is 1 to 1. So the numerical method, the Schwarz-Christoffel mapping, does the mapping from the canonical domain to the physical domain. Okay, right? So, and in the numerics, you can do the inverse mapping. You can go from Z to W also, but it's defined in this way. So here's the canonical domain, and you map it to the physical domain. This is how the derivative of the mapping is defined, okay? The derivative of the mapping is basically this product. This little c is some scaling factor, okay? Right? If you multiply something by a constant, that's still a conformal mapping, right? And you have these hyperbolic signs. I'll show you just a second why. Each of these guys have an AK. What is the AK? AK is a pre-image of a corner, of a vertex, okay? And each of these signs goes to a power alpha k minus 1, where alpha pi is the internal angle, okay? So for example, for this case here of the arrow in red, alpha is 3/2, okay? For this corner here where I'm pointing now, alpha would be 1/2 because it's pi over 2. So it's the internal angle. So this formula is the formula how the conformal mapping is done for the strip map. Okay, there's in this package, which is free. I'm going to give you either today or next class the how you download it from Toby Driscoll's webpage. Okay, so what the numerical method does, it has a nonlinear numerical solver, because it's a nonlinear system of equations that it builds, numerical solver to find the pre-images of the corners. Once you found the pre-images of the corner, you're done. You know the mapping, because the angles, we know what it is. The angles are here. What we don't know is, and it's very sensitive, is where is the pre-images of these guys. And there's a phenomenon in numerical conformal mapping. There's something called crowding, which is a numerical phenomenon. Which happens, and actually, I played with, which happens like this. You can see that in that little booklet in Portuguese that I think I shared with you of the colloquium with Eileen, we have these things, right? Which is like this. If this part here is very elongated, these two nodes here, these two corners here in black next to the arrow, they get exponentially close here in the canonical domain. And sometimes they get so, if it's very elongated, like this ceiling of the bottom, gets very elongated, and these two nodes here where my fingers are in the canonical plane, get so close together, exponentially close together, mathematically it's still 1 to 1, right? That's conformal, that's a complex variables. But numerically, they get so close to each other that the method cannot make a distinction between them. And that's why it's called crowding. The points get crowded, and you don't know if you have 1 or 2 points or whatever, and the method breaks down. Okay? So that's what crowding means. Okay, so this problem of finding the pre-images is the hard part. But after you found that, you basically have your expression here to use, and the Schwarz-Christoffel toolbox will compute all these guys for you, okay? Okay, so that's how the method works. I mean, what the numerical does. I'm not going to tell you, basically, it's an iterative process which kind of compares the lengths in both domains and does ratios and so on and generates a nonlinear system. That we're not going to get into. If you want, you can, in the book, this book, it's explained. So here is just an indication of why this hyperbolic sign comes in. Because in this toolbox, in the book, in the MATLAB free software, it's free, right? You can map onto a strip, you can map a polygonal domain, right? That's why it's Schwarz-Christoffel. You can map a polygonal domain onto a strip. Actually, before you map it onto a strip, usually you map it either onto a half plane or onto a circle, onto a disk, right? And from the disk or the half plane, you go somewhere else, right? Okay, so what the hyperbolic sign does, it's an exercise in complex variables, it basically, what it does, it basically gets the strip and maps onto the half plane with a slit. And then with the power, this power, what it does, it maps this onto that. Because if you have a power like square root, right, divides the argument by 2, right? So let me, I think in the next, here it is, oops. Here it is, see? I just added these colors to show what happens. So when you use the sign, it sort of closes the upper part into that slit, that double-sided, and then with the angle, right, it cuts like that. And that's just to explain how the hyperbolic signs come in. Oops. Okay, that's just saying that it's good. Okay, now, look, this is the derivative. This is the formula, Schwarz-Christoffel formula for the derivative. Well, by Cauchy-Riemann, we also know that the derivative is equal to this, right? And if we want how do I get the Jacobian of the map along this dashed line here, which is my free surface of my water waves? Well, the Jacobian of the map is the absolute value of this guy squared. Right? Check that. Right. What is the absolute value of this guy squared? Is this guy squared plus this guy squared. And that's the Jacobian using Cauchy-Riemann. Because dx dxc is equal to dy d zeta. Right? So therefore, I can write the Jacobian is just the absolute value of this guy squared. Okay? And this guy, the Schwarz-Christoffel toolbox gives it to me. So you see how easy it is. After you understand, basically you get something just typing a few commands, like 4 or 5 commands. Okay? Okay, let's keep on going. Let's see how far I can go today, or else I come back next time. So my coefficient m of xi, which is the square root of the Jacobian, is nothing more than the real part of the derivative evaluated on the free surface. That's all I have to do. Okay? So the Schwarz-Christoffel toolbox. So there's many ways you can use the Schwarz-Christoffel toolbox. The first one, which is the fun part, now I don't use it anymore because I need to make things more automatic. But if you're using for the first time, and actually if you want to show it to a friend that's learning complex variables, this is the best way to use what's called the Schwarz-Christoffel GUI. Right? So see, here it is. Schwarz-Christoffel graphics user interface. So if you type, this is the MATLAB prompt, right? You download, I think it will appear here in a second. If it doesn't, I'll give it to you next class. You download from Toby Driscoll's homepage. I just did this last week because I was needing it for some research thing, and I wanted to see if I had I wanted the latest version, which is basically similar to the one I had before. You download this, zipped package, you open it, and then you run MATLAB. The easiest way to do is that you run MATLAB on that directory, okay? If you want, you can install it as a package. I just run it in the library so it finds all the Driscoll MATLAB files, M files, okay? So if you type this scgui : there, it opens a window where you can play with a mouse and do conformal mapping. I think I have the pictures here. So here it is, see? it opens this interface, graphics interface, where you can say, look, just with a pencil, with a mouse, draw a new polygon. So you draw a polygon. Toby Driscoll is not only a very good applied mathematician at the University of Delaware, but he's one of these guys, young guys, younger than me, not so young anymore, but that loves to program and is a whiz with MATLAB, right? Knows very well MATLAB. So he generates all these commands, so you can draw a polygon just by clicking on the screen. You can modify it with eraser. Then when you press this, and then here you choose which kind of mapping you want. Here you can't see well, but if you open this, you would see which mapping you want. Like, for example, strip map. It maps onto a strip. Disk. It maps onto a disk, okay? And then you can also plot the orthogonal mesh, right? You can set where you want your center of your mapping, where you want to put the origin, and other things. And then also you can press a button to see the exact values of where things went. Let me show it to you. Okay, so this is just to generate, see, polygon variable. Okay, and then here are the command lines. So you can also do the mapping. So let me actually show you both ways. You can also do the mapping. This is how I do now, because I need to make things a little more automatic than clicking by hand and so on. So you can also do the mapping like this. I don't know if you can see this well. Z, I don't know if on the video how good this is. Can you see, Lucas, more or less? Let's see. So, okay, so this is Z are the coordinates of your polygon. So for example, this Z here is minus inf, because the method needs for you to put a node at infinity, at minus infinity. That's just the way it figures out. So minus inf is a node that's out in this way. Plus inf is a node that's out that way. And then these are the positions in complex variables of these corners, these nodes. And alpha are the angles, like a half, 3 halves, and so on. Okay? Then after you define these two guys here, you define this object P as a polygon with coordinates Z and angles alpha. So you just write that P is equal to polygon, and you click, then MATLAB, this code creates an object, a little bit like C++ kind of things, right? Creates an object that is a polygon, right? What is the polygon here? The polygon is this infinite strip, infinite quote unquote, right? It knows that it extends uniformly far away. So it's this infinite strip with these indented parts, okay? That's the polygon. Then I do this command, F is equal to strip map P. So very easy, right? What that does is that gets this object P, a polygon, and does the strip map, which means maps this strip with these corners onto a flat strip of unit height. It puts it always as a target strip, a strip of unit height. And in this other object, F, it saves the mapping, information for the mapping. So F is your mapping. Okay? Then here, if you do this and you don't put the colon here, the half colon here at the end, right, it prints information from the map. Let's see the information from the map, what it is. It says the following, that the Schwarz-Christoffel strip map found the following. Found these vertices. It is correct. Look, it starts from here from the bottom, minus infinity. Then it goes to minus this is 0, this is plus a half. I don't know where the origin is now. I can't quite read it. Anyway, so I don't remember if it's going. I think it starts from the bottom and then it loops up to the top. And then, so here we can't read it well. Maybe, in the book you can read it better, or maybe even if you look at the video. And then here the C is the scaling factor, and this is the apparent accuracy found through the iterative scheme. So the apparent accuracy is like 10 to the minus 9. So you have like 9 digits of accuracy, more or less. That's pretty good. For what? For the pre-vertices. So see here, so this is the coordinates of the vertex that I gave the mapping. This is the alpha, the angles we gave the mapping, and this is the pre-images that it computed. The pre-vertex is the pre-image. Okay? And then if you do plot, so see, I haven't shown you many commands, right? Look, just a few commands. Coordinates, angles, create the polygon, create the map, you're done. And then there's going to appear on the screen something you have to click on the left infinity, the right infinity, and so it's simple. If you play with this and you have trouble, I mean, you can ask me. And then if you do plot F, the mapping, and you ask for 30 lines in one direction and 10 lines in the other direction, this is what you get. So it plots the level curves. So what this is doing, it's plotting the map, it plots this, the level curves. So here is an example, very simple example. So if you don't want to type very much, for you to play on your own, right? Here's just a triangle on the bottom. I haven't reflected the domain, it doesn't matter. Here is the coordinates. Here's the angles, and you do the strip map and so on. Oops. So go to MATLAB. Well, we're already going to MATLAB. I don't know why I mentioned this here. So here's doing more complicated things. Yeah, now I'm going back to waves and papers. Recent research, yeah. I'm going to go, I have a few minutes. I'm going to go quickly to recent research. Well, I'm going to, let me just see, where do I have the web page of Driscoll? Oh, here it is. Sorry, here it is. For some reason, I skipped this. I'm sorry. So this is the web page of Toby Driscoll, University of Delaware. The page still looks pretty much similar to this. And you here, see, you click on this, it will ask if you're using, I think, Windows or Apple, and you download things. And that's it. You just open this zipped file of a few mega in your directory. You open MATLAB there, and you start playing. And it's a lot of fun. And it generates beautiful graphs. So all these graphs I generate, still today I use these graphs for things related to my research. Okay? So he also, together with Trefethen, have been developing this other software which is called ChebFun, which is something related to Chebyshev functions and approximation, spectral methods, and so on. So it's another source of free software. This one I have never needed to use, but should be very good too, because Toby is very good on programming in MATLAB. Let me, in the last minute, then let me go to maybe one thing to show here. So this is something that actually Christian is actually reading a little bit about, which is another research which I have interest, which I use conformal mapping also in a way where there was no Laplacian, there was no invariant operator, because if I do conformal mapping with Laplacian, Laplacian remains invariant, because Laplacian harmonic function is the same. This is for this problem of waves in channels, like this. Whoops. Like this. So we did first with the Vanessa, we did first in an L-shaped channel, and also in channels like this region here, which is a forked channel region, not with the island, but just the branching. And we used conformal mapping to make the domain simpler, and we got very nice results doing that. So in this L-shaped one, we actually just made it a uniform strip, right? There will be singularities here and here in the Jacobian. We put the singularities just a little bit outside the fluid domain, and we got very nice results. Let me finish just showing to you some things here. So this is two papers that we used that did the numerics using finite difference in this original domain, but they had limitations. They could only do certain things, and the application for this problem was actually, for us, the application of this problem was this. A Norwegian researcher once mentioned to me that in Norway, they have serious problems sometimes with tsunamis in fjords. There's avalanches of rocks, generates a wave, and actually in 1934, right? I forgot the date. There was this thing that destroyed the whole city. Where is it? Oops. Here it is. Yeah, 1934, Tyfjord. Look at the city before the tsunami and after the tsunami. Many, many kilometers away, there was this huge avalanche of rocks. It went through this sort of network of channels, which are fjords are basically things that come from the ocean. And the wave reached, like after traveling many kilometers, the wave reached the city, which actually was in a narrower part. The wave was 16 meters high and killed 40 people. Look how dramatic. So the Norwegian Geophysical Institute or whatever, they do the surveillance and they use models and so on to check, how things, what's happening, and they got to be aware so they can tell people to get off right near the fjords and so on if there's a landslide. So what we did, conformal mapping, and I'll finish here, I have just a few more minutes, is that we then studied using conformal mapping this abrupt turn, this Y-shaped symmetric and this asymmetric channel, and we solve it in the canonical domain, which is, well, this one, we map it to this. This one and this one, we map it to a strip with a slit, which means if the channel, if I do the mapping, look at my hands, this is the Y. If I do the mapping, when I close it like this, there's a slit here, okay, just like in the branch cut. So that means over this line, I have the upper side and the lower side. The upper side controls this part, the lower side controls this part. And then we did something more, which is we averaged the dynamics, right? And we were able to then reduce this two-dimensional domain to waves on a graph, which is something I'm still very much interested in. So Christian in his seminars is presenting things along those lines. Okay, so we use conformal mapping. And just to finish, and this is how it works. See, if I map, this is a polygonal shaped domain, right? So I can map it to this domain. And those people who did the numerics before us, they had limitations that they could only do branching regions that were either 45 or 90 degrees, because that was the only angles that would fit their finite difference grid in a nice way, okay? Because say if you have a grid, right, let me do it very quickly. If I have a grid like this, I can then put the channel, say, branching like this, going through the nodes, okay? My drawing's not very good, but you understood, right? Well, with the conformal mapping, we can do any angle. Why? Because we map this region to this. Here we have the finite difference that's boundary fitted very well. And where is the information of the angle? The information of the angle is in the Jacobian of the transformation. In all the other 1D models, graph models, none of these models, I've talked this with Christian, right, do not have information of the angles. And our model does. So let me see if I can show you maybe the last few slides, one or two. Okay, so anyway, we reduce, right? We want to do numerics now on a model like this, 1D. And let me see, I think I have, let me see if I have, I just want to show you the graph of the Jacobian. Maybe I don't. Maybe not in this picture here. Oops. Oh yeah, here it is. And you see, this is the last figure. These graphs are generated by Schwarzkopf toolbox. So if I have a channel like this coming this way, and depending on this angle, this is Jacobian. If the angle is 30 degrees, this is 1, 2, and 3. If it's 60 degrees, it's like this, and if it's 90 degrees, it's like that. So you see that the coefficients change. And the nice thing is that the Jacobian very quickly goes to a constant. So conformal mapping using the Schwarzkopf toolbox, very useful for also this problem of waves in channels in a situation where the conformal map, the operator, the differential operator, is not invariant under the conformal mapping. It changes. But who cares? I'm just doing a change of variables. And I'm doing a change of variables that's convenient for the problem. So, right, again, the Schwarzkopf toolbox, very, very, very convenient. And as always, that's amazing, generating very beautiful pictures, right? This is very easy to do. I haven't showed to you, but basically, anyway, it's very simple. If you want to compute the inverse mapping, the mapping, there's a command that's eval, like this. That's another book. So if you want to start, eval f on some, it's not complete, the command, okay, but eval the mapping on some grid. You can sort of think do eval inv, which is the inverse map. The command, I think this one I'm not so sure if it's correct out of my memory. And there's eval diff, which computes the derivative of the map. So all this is very simple, okay? And if you download, Driscoll's package, it comes with a manual, right, instructions and so on. And also if you read that little booklet in Portuguese of the course here at IMPA, which I think I sent to you, there are some instructions there how to use and start playing, okay? So I'll finish here, and next week we come back to some other stuff.